Good morning, everybody. It's a pleasure to have such a meeting at the Institute of Advanced Studies. First of all, I would like to thank Professor Christopher Small being here and Professor Ligia, who made possible that such event could happen in our institute. We have a great interest in geography, especially in the context that one of the priorities of our institute is to assemble a comprehensive research program on cities and quality of life and human health. So we encourage, and the geography department was very responsive in this aspect by providing us with the opportunity of doing precise diagnosis or trying to identify in shapes, occupation, functions of the city. Indeed, I am a very primitive person. I am a physician and a pathologist. So I see dead people. And from inside, we have the tragic privilege of seeing how inequalities across city influences our health. So it's a, let's say, macabre observatory, but very precise. So we are trying to combine data for mortality of the city, including that obtained at autopsy. So we have performed a large number of autopsies in our department, 16,000 per year, and geocoding, and trying to identify markers of exposure, personal habitats, but also their habitat. I asked Ligia to introduce more efficiently Professor Small, but I made an incursion on the web of science, and I just typed cities. Columbia University ranks first in terms of publications. But interestingly enough, the second is the University of São Paulo. But I understand that in Columbia there was, so they produce a lot of bricks, but the bricks are ordered in such a way that they build a building. So there's a project. So they can integrate the different pieces. In the University of São Paulo, the process I think was opposed is bottom up. There is no central organization, so we produce many bricks, but we don't accomplish the integration of them, so we can erect large constructions. So this is the process. And interesting, the New York University is third, and Mexico is the fourth. So cities with problems, personality, shape somehow our mental properties that made us to be interested in cities. So here we are trying to erect bridges of knowledge, and doing not multidisciplinary research, because multidisciplinarity is necessary but not enough to melt like bacteria does, to modify, incorporate genome characteristics, making something different. The difference between Japanese cuisine, multidisciplinary but doesn't mix, and French cuisine makes a lot of difference. So this is the reason that we are not only personally but also institutionally interested in expanding the role of geography in urban scenario for many purposes. So it's very important for us to have Professor Small here. And please, Ligia, introduce Professor Small. And thank you very much again for the presence of everybody.
Okay. Good morning, everyone. Thank you for coming. We are here together. First of all, I would like to thank the director of Instituto of Advanced Studies of USP and the staff for the organization of this meeting. And I would like to make a short introduction about the theme. Professor Saúde already made a really interesting point of view. We are here because we want to link urban morphology to some health outcomes in São Paulo, mainly. We are very interested to know how the length of blocks, the verticalization, the presence of green areas, microclimate can affect health in several ways. We have already some papers saying that linking air temperature and microclimate to some infectious diseases in the city, like the occurrence of dengue fever, mainly in the hottest areas of the urban area of São Paulo. We also have some studies showing that respiratory diseases are associated to some vulnerable population, like elderly and children. We also have other studies trying to see how urban morphology can affect promoting or inhibiting physical activity, and it could affect also some hypertension, diabetes, obesity in the population, and also coronary disease. So we are trying to extract information from the satellite images and see some variables that could be used to better understand the relations between the morphology of the city and health. Of course, we can't think about urban environment if we don't think about the historical process, the political, economic, and social process involved to build the city. But here now, today, we are just looking at this built environment and how it can affect health. So we have the pleasure to have here two people very experienced in remote sensing and how to extract and what variables could be used to think health in São Paulo. We have Professor Christopher Small, as Professor Saldiva already introduced you. He's from Lamont Doherty Earth Observatory from Columbia University. He's geophysicist, so he's very interested in spatial-temporal process changes and process and how they occur in the causes and consequences of these changes in urban and non-urban areas and all over the world. And he can say a little bit more about this. We also have a geographer, Marcos Reis Rosa, there, who is a PhD student at graduate program in physical geography and has more than 20 years of experience mapping and using satellite images to map land use, land cover changes in urban and non-urban areas. And he also tried to show us how we could connect the results of his maps to try to understand health. And also we have Associate Professor Reinaldo Paul Pérez Machado from the Department of Geography, USP, who is a geographer also. He works with cartography and makes some research on urban indicators and using remote sensing, using geographic information system, in studying social indicators and linked to urban geography. The dynamic of this meeting here, we will start with Professor Small, who will make his presentation during about 40 minutes. And after that, Marcos will make his presentation. And after that, Professor Reinaldo will make some comments and questions. And we will open to the public to make comments and questions, okay? So I hope we enjoy and can make this link. And start with Chris.
Thank you. Thank you all for inviting me. Very happy to be back in Sao Paulo for the first time in now 3 years. Oh. Can you hear me? Okay. Thank you all for being here. I will try to make it worth your while. All right. This morning, what I'd like to talk about is a kind of an unusual application of remote sensing to trying to understand an important aspect of the urban environment. And specifically, I'm going to talk about vertical growth of urban areas in 3 dimensions. So, rise of tall buildings, and the effect that these tall buildings can have on the transfer of energy, the influx of solar energy, and how that may affect the microclimate. Different types of urban morphology and how they may affect the ground level microclimate for the people living and working in the cities. So this is brand new work. I just made the presentation this morning, and some of the research that I'm going to show you has just been done in the last week. And some of it has been done a couple years ago in collaboration with Ligia and Hinaldo. And I'll also show you some imagery from a new satellite that has just recently become available. And I think the combination of these satellites together will provide very useful tools, hopefully for all of us, to better understand the urban environment. So I think that I've covered all of the points here. Okay. Can you all see this okay on one of these screens? Because the angle I'm seeing it from here, there's a lot of glare from the windows. But, okay. So I trust you recognize what we're looking at here. This is a satellite image of Sao Paulo and the surrounding areas. This is a combined visible and infrared image. So this is not what you would see if you looked out the window of the space shuttle. The colors are more saturated because we're combining visible and infrared information here. It's basically just reflected sunlight. And the colors that you see here are not natural colors, but they're artificial colors that tell us something about the absorption and reflection of different wavelengths of infrared and visible light. So this is actually the first cloud-free satellite image collected by the first Landsat sensor of Sao Paulo. And this was from, I believe, Julian Day 95 in 1975. So it's a little later than this time of year in 1975. And you can recognize different parts of the city. You see some difference in the color within the city. We'll look at this in more detail in just a moment. So this is what the city looked like in 1975. Oh, too many. Okay, 1975, 2000, and this was taken about 2 weeks ago by Landsat 8. So 2017, 2000, 1975. Now, you notice a couple of things. First, most obviously, the city's growing considerably. This is, the scale here is 90 kilometers across the horizontal dimension. And you notice, in addition to the growth, you'll notice especially between 2000 and 2017, the color changed. Now, this is not because people painted their roofs or something like that during this time. There's two reasons why this happened. One is because this image from 2017 and this image from 2000 were collected at different times of the year. So the illumination is different. The sun is in a different place. This was collected around Julian day 240, so I guess that would be your springtime. And this one was collected just about 2 weeks ago. And so even if nothing had changed in the city, the images will look differently because the sun is in a different place, and so there's a different amount of shadow and different surfaces are illuminated. And this is basically what I'll be talking about for the next few minutes, is the effect of different illuminations on different types of urban morphology. So before I do that, I want for you to compare this image to this image. These were acquired at exactly the same time by the same sensor. This image is a visible image. So the colors that you see here are more or less the natural colors, what you would see if you looked out the window of the space shuttle. And you see there's not, it's very high contrast, but there's almost no color. It's mostly shades of gray. And the darker areas, it's a little hard to see, but the darker areas are actually green. So they're vegetated areas. And this illustrates one of the reasons why we use visible and infrared light together, because things that look the same in the visible often look very different in the infrared. And so we can distinguish, for instance, different types of vegetation in the infrared that look the same in the visible, different materials, different building materials. And so what you see here, this is one of the ways that we compare different satellites. The curve that you see here, the gray area, okay, that doesn't, hold that thing, please, thanks. It just doesn't show up against the screen. The gray area that you see here is a graph of atmospheric transmission. And so the higher the value of the gray, the more light comes through the atmosphere. And in the areas where the graph goes down, most notably in here and in here, these are wavelengths where the atmosphere absorbs almost all the radiation. Specifically, it's the water vapor in the atmosphere that's responsible for most of these absorptions. And so at some wavelengths, not much energy gets through, like here. And other wavelengths, like here, almost everything comes through. So we refer to these as atmospheric windows. And this is showing the visible part of the spectrum down here between 400 and 700 nanometers, where you see the red, green, and blue. This is the part of the spectrum where our eyes are sensitive. And everything beyond here, everything longer than 700 nanometers wavelength, is the infrared. And so at these wavelengths here, infrared light behaves exactly like visible light. It's just a different wavelength. Our eyes don't see it, but it behaves the same way. It casts shadows and illuminates in the very same way. Further out here, there's a piece of the graph taken out here, and this part of the infrared here is the thermal infrared. And so I'll show you some images collected by these same satellites in the thermal infrared wavelengths later. The difference here is that the thermal infrared imagery is not emitted by the sun, it's emitted by the Earth. So it's the visible and infrared light at the shorter wavelengths that comes from the sun, interacts with the Earth's surface. Some of that energy is absorbed and some of it's reflected. The part that's absorbed, the energy has to go someplace. The absorbed energy is emitted again at thermal wavelengths. And so this is emitted heat. It's basically the heat that you would feel emanating from the ground. And this is important because this heat, this absorbed radiation, contributes to the air temperature that we feel when we go outside and walk around. And most notably in the summertime, when it's hot out, part of that heat that you feel is being emitted by all the buildings and the ground surfaces surrounding us. And so this is this is one of the things we're interested in understanding is how the urban morphology influences the energy exchange between the incoming solar energy and the re-emitted surface temperature. Okay, now we've zoomed in a little more closely here. I trust you recognize where we are. Now you're seeing this image at the full spatial resolution. So 1 pixel on the screen is equal to 1 pixel that the sensor imaged. So this is as much detail as we get from this sensor. This is the same Landsat scene that you saw from Landsat 7, collected in 2000. The same wavelengths. This is visible and infrared. As you may have noticed already, the green areas are vegetated areas. They're very bright, they're very reflective in the near-infrared wavelengths, around 800 nanometers. And what you notice, as you look at the built-up parts of the city, you notice the color changes. Both the color and the brightness change. They vary throughout the city. And this is, again, this is a function not only of the building materials used, but also of the illumination and the three-dimensional structure in the shadow. So this is the image from the winter of 2000, or the springtime of 2000. And this is the image that was collected a couple weeks ago by Landsat 8. Now, Landsats 5, 7, and 8 are intercalibrated, meaning the measurements they make are connected to each other. They're calibrated across sensors so that we can display images from different sensors in such a way that the colors mean exactly the same thing. And so now when you see a difference in color here, that's a real difference. It's not just a difference of enhancements. That's really a difference in the light that was reflected and measured by the sensors. And so why is there so much more contrast in this 2000 image than in the 2017 image? Has to do with the illumination direction. In part. Also, in some areas, most notably out around the peripheral areas, the peri-urban areas, some of those changes are actually due to differences in the land surface, where the land cover has changed. I'll show you an example of that in just a moment. So now, to give you a preview of one of the new satellites, we're going to zoom in to the area near the center here. And again, 1 screen pixel will be 1 image pixel. And so things are going to get bigger because this sensor has higher spatial resolution. You see the difference there. This image was collected by the Sentinel-2 satellite. This was I believe this was last summer. I don't remember the exact day. You notice the colors are similar. They're not exactly the same. This satellite hasn't been calibrated to the Landsat satellites yet. We're working on that now. But what you notice is with this satellite, you can see, or with this image, you can see individual buildings. And this is because the Sentinel-2 satellite has a spatial resolution of 10 meters, whereas the Landsat sensors have a spatial resolution of 30 meters. And so the difference between 10 meters and 30 meters is really important in urban areas because the spatial scale of buildings and roads is on the order of about 20 meters in most parts of the world. And so at 30-meter resolution, the different features are mixed together in what we call mixed pixels. With 10-meter resolution, we're able to resolve individual features like buildings and roads much more clearly. And so this is the Sentinel-2 satellite was launched by the European Space Agency it was launched in early 2015, but it had to go through a testing period. It began returning usable imagery in late 2015, in August 2015. And in addition to having finer spatial resolution, it has more frequent repeat. Whereas the Landsat sensors revisit the same place every 16 days, Sentinel-2 images every place on Earth every 5 days. So we can see finer temporal scale changes with Sentinel-2. In addition to that, we'll go back here, and these bars that you see, these horizontal bars, show the different wavelength bands that the sensor is able to measure. And so, for instance, Landsat 7 and Landsat 8 were designed to be similar so that the data could be compared. And so what you see, the way to read this is Landsat 8 has 3 visible bands, or visible red, green, and blue, just like a digital camera. It has 1 near-infrared band, mainly used for mapping vegetation here. And it has these 2 bands, these 2 channels in the shortwave infrared. In addition, it has 2 channels in the thermal infrared. So for comparison, Sentinel-2 has 4 channels at 10-meter resolution in the visible and near-infrared. And it has 2 more channels in the shortwave infrared, and 4 more in the near-infrared. And then 1 more visible at 60-meter resolution, and these 2 channels also at 60-meter resolution, designed to be able to measure the absorption from the water vapor in the atmosphere. And so Sentinel-2 has not only higher spatial resolution, more frequent repeat, but it has 13 spectral channels instead of just 7. So the more spectral channels the sensor measures, the more different colors can be represented. Many, many more colors. In fact, effectively, every time you add 1 more spectral channel, you double the number of colors you can possibly represent. So this new Sentinel satellite is able to resolve much smaller features, many more different colors, and much shorter period temporal changes, because it images every 5 days instead of every 16. And as if that weren't good enough, there's going to be more of these Sentinels. They're going to put up, I believe, at least 2 more. So that revisit time, when they're all up and operating, should approach 1 day for most parts of the world. So we'll be able to resolve processes in time and in space with much more detail than we can now. This is what's coming. This is what's going to happen in the next few years. The amount of information that we're going to be getting from these satellites is going to explode. And with that, the number of different types of problems that we can use these as tools to try and solve will increase also. Okay, so one example of how we use these data. These images are taken from the Landsat satellite. One thing we do is we take these spectral bands that I just showed you, and we like to convert the spectral information into something easier to understand, easier to interpret. And so what we do is we have a what we call a mixture model that enables us to take the aggregate, the mixed reflectance within a single pixel, and estimate within that pixel the total amount of the area of the pixel that's covered with vegetation, the total amount that's covered with soil or impervious surfaces like roads or roofs, and the total amount of the pixel's area that's dark, that is either absorptive or not illuminated. And so what you see here are the results of this estimation. In this case, in the red channel, this is the amount of what we call substrate, which would either be bare soil or impervious surface, like roads and roofs and things, basically bright surfaces. And so the brighter the red, the more area of that pixel is contained with substrate. This is the same thing except for vegetation. So the brighter the green here, the more area of each pixel is covered with vegetation. And here, the dark, in this case, it's usually either something transmissive and absorptive like water, or a shadow. So in the case of an area that's not illuminated, it appears dark. In the case of water, light transmits in and is absorbed and doesn't come back out, and so it appears dark. And also materials that are naturally dark, like tar roofing or freshly paved asphalt also appears dark. And in most cases, in urban areas, this dark fraction corresponds to shadow or very dark surfaces. But even streets, if you notice, after a street's paved with asphalt, it only stays black for maybe a few months because the asphalt weathers and it becomes lighter and lighter, and eventually if it isn't resurfaced soon, it will become almost as bright as cement. So most of what we see when we're looking at the dark fraction in an urban area corresponds to shadow because of the three-dimensional structure. So we take the reflectance measurements that the satellite collects and we use them to unmix each pixel to get the total amount of substrate, vegetation, and in the case of urban areas, shadow. And we combine the red, green, and blue channels together to make an image like this. And you notice this image has more bright saturated colors than even the infrared images I showed earlier. And that's because it's separating the materials more effectively. It's giving us more information in a way that's simpler to understand. In this case, we've taken 6 spectral bands corresponding to reflectance, and we convert it to basically three maps that tell us how much of each pixel is covered by a different type of material. So it's easier to interpret. So what we've done here is we've made one of these composites for 1990, one for 2000, and one for 2015. And in each case, then we take just the dark channel, just the shadow map, and we combine it so that the shadows for 1990 are in red, 2000 are in green, and 2010 in blue. And so any place where the shadow hasn't changed appears a shade of gray, equal amounts of red, green, and blue. Any place you see color implies some kind of change in the shadow. And so what you notice here is this sort of blue halo around the peri-urban areas, around the edge of the city. What that means is that those areas became darker. But these images were collected at different times of the year. So the effect of the illumination of the changing sunlight should be canceled out in this case. And you notice almost every place else in the image is a shade of gray, meaning the fractions hadn't changed. But there's this band of blue going around the edge. And what we interpret from this, the one thing that could have changed is the amount of shadow. And when I was here last in 2014, we went out to some of these areas, Ligia and Hinaldo and I, and looked at what the land cover looked like in these areas. And also compared some high-resolution satellite images. And what we see, sure enough, is more vertical growth. Not only more high-rise, like what you see on the left here, this you probably recognize as Morimbi. And so between 2004 and 2014, a lot of vertical growth, high-rise buildings. But also here in the northwest corner of the city, you see low-rise development. But you see all this infill development. All these bright areas here were not intensively developed in, this is 2002. And just a few years later, the development filled in these open areas. In addition, we could see from the houses, the buildings in these areas when we went there, could see that it looked like the ground floors looked different from the second stories. And apparently what happens in these areas is people add floors to their houses. And so you think about it, if you have a one-story house and you add a second story, you've doubled the height of the house. And so under the same illumination conditions, you've doubled the amount of shadow that it casts, the length of the shadow that it casts. And so this is how, even with low-rise development, even just going from 1 story to 2 stories, we increase the amount of shadow. And So that's what we think is causing this blue halo is low-rise development. Now, of course, in areas like Morumbi, you also see it's smaller, but you also see increase in shadow there. It's just harder to see at the scale of this map. So this was kind of surprising to us that we could use satellites to see the effect of people adding stories to their houses. But we can't come up with any other explanation for how this darkening would be happening. Aside from the fact that some of these areas where there's exposed soil, it tends to be brighter. And so when you pave over exposed soil, that does make it darker also. But the thing that we saw on the ground was it looked like people were adding floors to their houses. Now, these images also point out some of the limitations of trying to use this very high-resolution imagery, like what you see in Google Earth, this very detailed imagery. Trying to use this kind of imagery for change analysis is more difficult than you might think, because these high-resolution sensors look at different angles. The sensors like Landsat look straight down, and so every time Landsat or Sentinel passes over, it's seeing the same place from exactly the same angle. The high-resolution sensors don't do that because they can point. They can look off-axis of the track. And because the companies that own these satellites are trying to collect imagery for sale, they take orders and they do what's called tasking the satellite. And so when a satellite, one of the commercial sensors, passes overhead, it's generally not looking straight down. It's usually looking off to one side or the other to image a specific target that somebody has paid to have an image collected for. And so if you look at this image, especially the image of Morumbi, very closely, you'll see that even the same buildings are leaning different directions because they're being seen from different angles. And so this makes it very difficult to do quantitative change analysis because you're seeing the same thing from different perspectives. And so this is one of the advantages of using the lower spatial resolution sensors like Landsat and Sentinel, is that they always see it from the same geometry. So here we are back again looking at the entire city. This is the 2000 image collected by Landsat 7. And so now you can see the variations in the brightness within the city are, for the large part, variations in the building heights. And again, if you remember the Sentinel image we were looking at a few minutes ago, you could see the actual buildings, and you could see some areas had more shadow. You could see the individual shadows from individual buildings. And so a lot of what contributes to the variations in brightness is the differences in heights of buildings. So now, if you look at this image and compare that to this image. This image is a surface temperature image. It's a thermal infrared image collected by Landsat 7 at exactly the same time. In this case, the colors correspond to temperature. And so the temperature scale is in the lower right corner. The temperature is going from 12 degrees to 30 degrees Celsius. And so we're seeing almost 20 degrees of temperature difference between the cool waters in the reservoirs and the hottest areas near the city center here. That's surface temperature. So it's contributing to the air temperature. And you notice, if we can flip back and forth, notice the difference between the red area here, the hot area here, and the blue cooler area here. It's not the right direction. Okay. Notice correspondence there. Now, if you look very closely, I think here in Jardin Paulista, and I think that's Paulista Avenue there, separating the low rise with a lot of vegetation, a couple two-story houses, to the high rises. And if you notice the change in temperature there, the area where the high rises are, oh, wait a minute, we have a problem. The images aren't lined up. Okay, I just noticed that. All right, well, just imagine that the images were lined up. What you would see, of course, it didn't do this morning on my computer. What you would see, though, is that this cool spot here is actually the coolest area corresponds to the high rises up on the other side of Paulista. And the Jardin down here, where the vegetation is actually a little bit warmer. And the hottest area here is around downtown, right? And so part of this difference, we expect areas with trees and more vegetation to be cooler, as vegetation transpires water and stays near the ambient air temperature. But what we're seeing here is that the coolest area here is the area where all the shadows are. Now, if you think about it for a second, that kind of makes sense. But often when people think about urban heat island effects, they think of the areas with the most densely built up areas as being the hottest. But in this case, the more densely built up area is actually cooler than the area with the trees and the vegetation by several degrees. So this is kind of a surprising result. I've not seen any mention of this in the literature before. And so we decided to look into this in a little more detail and try and understand what it really is the effect of the building height variation on the energy flux to the ground surface. Because if you think about it, the same amount of solar energy is coming, the same density of solar energy is coming into both places. But less of it is being emitted back up to the satellite in the area where the tall buildings are. And so that energy that's coming in has to go someplace. If a shadow is being projected from a tall building, the shadow is being cast over other buildings. Those other buildings aren't being illuminated. What happens to that light? That light hits the side of the tall building. So it's what we call sidewall interception. And so the energy that would be going onto the ground and onto the roofs of the taller buildings is being intercepted by the sides of the taller buildings. This changes the energy flux, right? Because if the building has glass sides, a lot of windows, that light transmits into the inside of the building, it's absorbed inside the building, and then the air conditioning system pumps the hot air back up out the top of the building like a chimney. And so that's energy that would be absorbed on the ground and would continue to heat the ground surface in the afternoon. Instead, it's being pumped out the top of the building hundreds of meters above the ground surface. On the other hand, some of it may be absorbed by the side of the building, but because that building's taller, it's going to be absorbed and re-radiated at higher than ground level, taking it away from where we would feel it on the street level. So here we're going to move to New York now and look at some experiments that we've done here. This is a Sentinel image that was collected in the summer of 2016. This was collected very close to, this is the very end of May, which is very close to the high point of our summer. And what you see is very little shadow here compared to September. Notice the difference. The colors didn't really change. The shadow is what changed, especially in this area here. This is Midtown Manhattan, where a lot of our tall buildings are. This is the financial district, also a lot of tall buildings. And these areas especially, you notice the shadow increase. Now look at what happens in December when the sun's at its lowest elevation. Now you can start to see the shadows of individual buildings being cast out over Central Park. So the sun's very low here, and we really see the difference now in where the shadowing is. And this is why. This is a building height map. It's from a digital surface model that was derived from a very extensive set of LiDAR measurements. These are airborne scanning laser measurements that make a very, very detailed elevation map. And so what you see here, the lighter colors are higher elevation. And so this is a way of validating that this dark area here is indeed building shadow. As you see, the buildings in this area are much higher. You see it extends down through here, and then down in the financial district, they get much taller again. And indeed, that's exactly where the shadow is. So we can use this. We can look in more detail at the effect of the shadowing using this elevation model, because we can calculate the illumination and the shadowing directly with the elevation model. It's simple geometry. And so what you're looking at here is a part of this model around the Columbia University campus. The campus itself is here in this area here, and the area surrounding it is a residential area in Harlem. And what you're seeing is a simulated illumination on this elevation model taken at 6 in the morning, just after sunrise, on Julian day 210, so in our summertime. And so what I'm going to do now is I'm going to step through a sequence of these going 1 hour later in the day, and so you can see how the illumination changes. So this is 6 in the morning, 7, 8, 9, 10, 11, 12, 1 in the afternoon, 2, 3, 4, 5, 6. And so you notice what's happening. The lighter the color, the more of that sunlight is being reflected back up toward the sensor. And so you see at the end of the day, only a very few of the tallest buildings are illuminated, because, and then the sides of the buildings, of course. And so this gives us a way of mapping in great detail where the energy is going. How much of that energy is being absorbed by the sides of the buildings versus how much of it is making it to the ground, to street level, versus how much is being absorbed by rooftops. So this gives us a way of understanding where the energy goes and where it's going to be re-emitted. So if we add this up, we integrate all of this over the entire day, this is what we get for the whole day. The lighter the shade here, the more energy is absorbed by that surface. And so this gives us a way of accounting in great detail where the energy goes, and therefore where it's going to be re-emitted later in the day. Now, why this is important is, well, as you all probably know, one of the consequences with heat waves, a big part of the health impact of heat waves is not to do with temperature during the day, but it's to do with the nighttime temperatures. So the nighttime temperatures don't drop enough so that people can sleep, then it adds to all sorts of physiological stress. And so when people tend to die during heat waves tends to be when they have several days of prolonged high temperatures at night, when it doesn't cool off enough at night. And that is in large part due to where the energy is being emitted and whether or not the ground surface can cool off at night. So we did the same kind of calculation. We added up what happened to all the incoming sunlight for different building geometries in different parts of the city. And you see here a comparison on your left between an area in Midtown Manhattan, a lot of tall buildings, and an area on your right is the area we were just looking at in Upper Manhattan, where most of the buildings in Upper Manhattan are maybe 10 stories or less, whereas if you see the height distribution histogram on the bottom here, in Midtown we have a much wider range of building heights. We have some very tall buildings that shadow other buildings there. And the plots on the lower right underneath shows the amount of time of direct illumination at each different elevation. And what you see is that most of the area at lower elevation is getting only a couple hours of direct illumination a day. Whereas in Upper Manhattan, where we have fewer tall buildings and less variation in building height, the distribution is more even, with most of the area getting about 6 or 7 hours a day. Now, if we compare that to more residential areas, this is in the borough of Brooklyn, where these are row houses, brownstones we call them, all about the same height, and the trees in between on the street are about the same height as the buildings. And you notice, overall, this image is much lighter in shade. These images, the Midtown image on your left is much darker, This one's a little bit lighter on your right, a little bit lighter still on the left. And out on Staten Island, which is almost a rural part of New York, the houses are only 2 stories high, 1 or 2 stories at most. They're much more widely separated. The streets are wider. And what you see is that more of that radiation is making it to the ground. So there's less shadowing in this area, more radiation being absorbed and re-emitted either at ground level or at roof level. And so that's going to heat the air closer to the ground and impact the air temperature there. So now if we compare that with some of these surface temperature images, what we're looking at here is a nighttime image on your left, or a daytime image on your left, and a nighttime image for a couple days later on the right. And what you see is that, and in each case, the warmer colors correspond to higher surface temperatures. What you see is, the thing to notice here is these 2 images don't look at all alike. The nighttime temperature is very different than the daytime temperature. And so the daytime temperature is dominated by the active emission from the incoming solar as it's being illuminated. The nighttime temperature, the sun's cut off, the sun's below the horizon. The nighttime temperature is telling us more about what's been absorbed over the course of the day. So we can use the kind of illumination modeling that I just showed you with the nighttime satellite imagery to try and understand how much of the incoming solar radiation is absorbed and re-emitted as heat. And you'll notice here the areas that were in shadow, Midtown Manhattan, financial district, the areas that are cooler during the day, you notice they're actually a little bit cooler than the surrounding areas during the day. They're actually warmer at night. So these areas, that sidewall interception is being emitted later at night, but it's being emitted higher off the ground because it's the taller buildings that are intercepting the radiation. So in a sense, you could think of these tall buildings as performing an ecosystem service for us, intercepting radiation and so that it would be emitted well above street level at night. So maybe an asset, for maybe a good thing about tall buildings. Okay, and finally, I just want to wrap up and show you one example of what's actually happening with the energy balance at street level. What you're looking at here are a couple of thermal images. These were actually collected from the window of my apartment, looking down on an intersection. I live on the 6th floor of my building, so we're looking down at a kind of an oblique angle here. And you can probably recognize some features. We're looking to the southwest here, and so the blue area here, this is a north-facing wall. This wall is never directly, or most of it is never directly illuminated by the sun. Whereas at the time this image was acquired, this wall here, it's east-facing, was being directly illuminated. You notice how much warmer it is. But you also notice much finer scale features. You can see people crossing the streets and the cyclists are several degrees cooler than the street because the street's been absorbing that sunlight for several hours already. You see the illuminated part of the sidewalk versus the shadowed part. You see temperature differences in cars. You can tell which cars have been running longer because the hoods over the engines are hotter. See, the tree is quite a bit cooler, even the part that's illuminated because it's transpiring water and keeping itself cool. And we see a completely different situation late at night. Now, none of this is illuminated. This is all just emitting the heat that the radiation it absorbed during the day. And you notice the street is still quite a bit warmer, in part because it's flat surface facing up. It's been illuminated for more of the day, especially in the intersection here. Now you see the tree is relatively warm compared to some of the building walls. Trees actually act as insulators because the leaves are full of water. And what we get from the thermography for each of these points here, we have a time series of temperature over 24 hours. And so we can look at the thermal cycle of different materials according to their orientation relative to the sun, as well as their composition and whether they absorb or reflect more radiation. And we're now at the point where we can use this type of ground level remote sensing to understand the energy balance and the energy flux at street level at spatial resolutions of centimeters, as well as looking at things like, for instance, ambient body temperature, surface temperature of people relative to the surrounding areas. And so where we intend to go with this, what I think will be possible for more people in the future, is to use these portable thermal cameras in combination with satellite imagery to monitor and keep track of how the energy flux is happening at street level and understand what is really the effect of, for instance, the tall buildings. And so why this may be important is because the number and diversity of tall buildings being built is increasing. Now, you know that here because you probably have more tall buildings than almost any other city in the world. You certainly have more than New York has. Whereas we have only a couple parts of our city that have tall buildings. You have tall buildings all over your city. So this is something you're obviously already aware of. But if you think about where the tall buildings are being built now, a lot of them are being built in China. And so what are the effects of all this vertical growth? Some of the effects in terms of the thermal environment, some of these effects may be positive. So I'll stop there. And I think I've actually said most of these conclusions already. Oh, and I should point out, I meant to mention this in the beginning, my collaborators, not only Hinaldo and Ligia and Elton, but also Chris Zappa, Dan Souza, and Anela Kure back at Columbia have all contributed to this work as well. Thank you for your attention.
Thank you very much, Chris. Wow, we have a lot of stuff to talk later. And now I'll ask to Marcos to start his presentation. I think you could change the place.
Thank you, Chris, for speech. Thank you for the invitation. I tried to talk in English. It's not perfect, but I believe we will survive. What I want to show is the next step. When we have all this data from new satellites and all the data from old satellites like Landsat, we have data from 1970 and 10-meter resolution from 1985, how we can process this data, how we can classify this data to produce some maps that we can use also in GIS and quantification. I want to talk about how to use cloud processing methodology. I will talk specifically about Google Earth Engine, but the concept is to process, to store and to process the data in the cloud, and what it changed in the methodology that we do remote sensing. Basically, in traditional methodology, we have to choose an area, choose the data of the image, download the data, download the image, calibrate correct geometry, and then mosaic the image, make digital process, classify the image to have the final product. With cloud processing, there is no new magic here. We have the same steps, but we can program these steps in the beginning of the process. And we set the location, the dates as a parameter in this process. So we can have the intelligence here programmed, implemented in programming language. Then we can choose an area, specify the parameters, run the classification, check the results, change parameters, choose another area, choose another dates, and then we spend more time here analyzing and checking the quality of our product. Then it's very easy to repeat this process. And I will show Google Earth Engine. Today, Google Earth Engine is free for use. It's free for academic research, and one can register and use it. It's a computer cloud processing. It has a data catalog of a lot of free images like Landsat, Sentinel, Mojis images, and they have tools to analyze this data. The interface is not so easy yet. You have to program it. So you have to program in JavaScript or Python. It's not easy to start, but when you know the objects, the tools that they have, it will become easier. I'll show two classification methods. First one, using Sentinel satellite images, based on supervised classification, on collect samples and classify the image. Second one, based on spectral mixture analysis and empirical decision tree. First thing, that's a Sentinel image here from São Paulo. We have in Sentinel a quality band that's try to mark each pixel that's a cloud. So we can remove these pixels, the cloud pixels from Sentinel. They are not masking shadow of these clouds yet, but we have methods to do that. Once we remove the clouds, we have in Google, not in Google, any remote sensing program can do that, but we can specify a time frame, get all the images in this period, and then use the best pixels cloud-free from these images. So we can build very easily and very quickly a cloud-free image from the area that you want to study. Another thing that's very important using cloud computing, we can use all the data, the reflectance bands from this image. We can use another index that's built comparing these bands, but we can use another kind of data that's the maximum value of the reflectance in this time period, or in the year. We can use all the images in the year and use the median, maximum, standard deviation. So it's values that will help us to understand how each target is being reflecting or it's being reflecting on the image. Well, here's an example. I collected just 3 or 4 samples of each of these classes. That's first grassland, wood, residential, vertical areas, industrial areas, main streets, and water. Just some polygons. These samples has about 500 pixels, so it's easier to use 2 or 3 samples. And that's the classification result. I'm using here, I'm not sure if I describe it, no. I'm using random forest. That's a classification that's a machine learning system that builds statistical decision tree, and they do it a number of times and then decide which class each pixel belongs. And here we have something that Chris was talking about. We can see the shadows here that's using this verticalization class. We can see here the forest and the area that's residential with woods. I will go a little farther here. And here we have here Paraisópolis, here Jardins, Ibirapuera. Here's the Sentinel image, and here the classification. Okay, we can also identify these areas that's very dense with no trees, no shadows, one house beside the other. And the areas that has more dense use and areas that has wood and residential, and areas that has verticalization buildings, like Brooklyn, here Brooklyn, here Paulista Avenue. A little far away, classifying all this area. And what's easier to use this technology? Because I just collected that samples in the main area. I can use, that's why Google Earth Engine makes it easier to process, to analyze this data. I can establish another region. The parameters there is the data that I'm researching and getting the images. And then I can classify this other region using the same samples that I used for São Paulo. And then I have here, let me check. I have here Campinas, using the same samples from São Paulo. That's the Sentinel image for Campinas. And then I got here the streets, the buildings, the buildings with high shadows, and the dense areas and residential areas and forests. The other classification method I explained using Landsat satellite, using historical data. I will show here. Just let me take my other. This is the method that we use in My Biomes. That's an initiative from research institutes and non-governmental organizations to map Brazil since 1985 to 2017. Collection 2 has maps from 2000 to 2016. Basically here we do the same logic to build an annual mosaic of the best pixels from Landsat. We establish the initial date, the end date, and the system will select the collections, remove borders, clouds, and shadows, generate spectral mix model, generate reflectance and fractions, median, generate index, and export this image with 28 bands. For each pixel has 28 informations. Based the same logic, we have here algorithm called fmask that will remove clouds and cloud shades. So we have no data where we have clouds or cloud shades. Another algorithm that will take the best pixel. In this case, we use the median value of all pixel values. And here, a simple explanation to why I use spectral mixture analysis. When we have here, we have two pixels. That's the University, Raio Olímpica. Here I have one pixel in Landsat and this pixel in a high resolution image. This pixel has 30% water and 70% of grasslands. And this other pixel has 70% water and 30% of grasslands. And they are mixed in the Landsat, and they have this value a little darker, the pixel above, because Landsat has a median value of all the existing objects in this 10-meter resolution. What the spectral mixture model tries to do is understand everything that is inside the pixel. So when I check this pixel, it will use a poor pixel of shade, vegetation, and substrate to identify this pixel has 35% of substrate, 30% of vegetation, 25% of shade. So we can use this data to understand what's inside each of these pixels. We have here the SVD model from Christopher, 2004. He used global end member for Landsat. And we have here Carl Souza that made adaptation of this index, these end members, to Amazon and dense forest, trying to understand one fraction soil, green vegetation, non-photosynthetic vegetation, that's wood, or basically wood, no green vegetation, and shade. That's the papers from Christopher Small and Carl Souza. And basically, what we do is process these images, and we have all the reflectance bands here, all the fractions band here, and index based on the fractions. So I can make normalization between green vegetation and shade to create some index. Some index that's very important, that's the variation of all images, of all pixels in all images during the year. That's what we call the NFI amplitude. So I will take the vegetation index and look all the images and see the minimum, maximum, and what's the variation. It will help me to identify what's happening in this pixel. Based on that bands, I can build a decision tree. This decision tree, I will look each of these pixels and make questions like one band. I can use here n of bands like slope, elevation, temperature. I have one first rule that's in the night light from VIRS, I can check how it's illuminated during the night. If it has no illumination during the night, I can say it's not urban. If it has illumination, I will check other variations. If it has annual variation during more than 100, this variation goes from 0 to 2000. It goes to not urban. Why? This variation happens in agriculture. When you have soil and growing vegetation, that's a vegetation index. When it has too much variation, it's planted areas. Here I use shade to define that's the main vertical areas. I check by shade. If shade is bigger than 90%, it will go for buildings. It's bigger than 95%, it's water. So we have here some confusion, so we have to treat it here. If shade is not that high, but the index between shade and green vegetation is high, I can go or as forest or urban woody. If green vegetation is high, and this is an index used to find forest. So green vegetation is high and forest is high, it's forest, otherwise it's grassland. If green vegetation is not that high, here I have soil and non-photosynthetic vegetation. If it has too much soil, it's just soil, otherwise it's urban. If the index between green vegetation and shade is not that high, I have or soil, or residential, or dense residential. Once I establish this decision tree, I can classify any of these images. That's a classification of almost all São Paulo state using these areas. So I have here the illumination that limits the area in urban. And I made a classification here each 5 years from 2000. So here's mosaic from 2000 and the classification from 2000. So I have here the forests, I have here Ibirapuera, Cidade Universitária, University City, Here, Jardins, that's the classification 2005, 2010, 2015. I can have the densification of the use in basically in any city. That's the main advantage of this technology. And I'm using the same decision tree in Rio de Janeiro. That's basically I'm online here, so I make this process online, it's not saved. What's saved here is the images that I use in map biomes. So I have images from 2000 to 2016. I establish here the parameters that I want, the years that I want to process, the biome that I want to use the image, and here is the variable that in decision tree that I can change because of to make an adaptation. I'm running the processing, and that's the result. That's what Google does. It will bring each area slowly because it's processing in each 9,000 computers around the world, and it will bring me the results. I would choose an area here. Let's see Maringá. That's the image. Let's go closer. I really miss a mouse here. And that's the classification that it's being processed on the fly. Okay, that's Maringá in 2000. That's Maringá 2015. You see how they recovered all this vegetation in around the rivers. I can check it on the image also. That's the image from 2000, image from 2015. So this classification, this is a classified image. Each pixel has one discrete value, 1, 2, 3, 4. So we can download it as GeoTIFF, convert to shapefile, and do statisticals and see what has changed. And this goes to all around Brazil. I can go. I can change the. Deixa eu cerrado. Let's see Brasília. It's not on the image yet. I'm happy. Yeah, it would happen if the image showed. That's the image from 2000 and the classification. And here, the classification from 2015. And we can see here new areas. And that's the pilot that has use, and they have woods also. Here the cidades piloto. There is no trees, and we can check satellites. We can check this area. That's the image from 2000, and that's the image from 2015. We can see how dense this area has become. That's the best use here is I can use my time to understand the data, to adjust the parameters, because I can just change any parameters from the decision tree. They are all here as variables. So if I want to check if the data from 2016 instead of 2015. So I have here the image from 2016. And the classification from 2016. I believe I have too little or too much vertical data here. In decision tree, what defines the vertical area is this shading variable 2. So if it has more than 90% of shade, it will go to vertical area. So if I change here, variable 2, instead of 90, I will change to 70, it will add in the classification much more vertical areas. Here's the center of Brasilia. If I add it, I'm back to 90. So, not sure if it was clear, but here we can look in details. Oh, here's the airport of Brasilia. So basically, this methodology is not new, but the way we work in cloud processing is new. I have easy way to build a cloud-free image using a time frame. I don't have to use one image. I can use all image from 2 months, 3 months time frame. It's easier to build index from these images and index based on this time frame or from all images in the all year. That in Atlantic Forest helped a lot because some agriculture in some stages look like forest. But when we use all the images in the year, we can see that there was soil, they planted, they grow, then they got green. Then they mixed. But if I use just one image, it can make some issue, but it's easier to build just all this index. It's easier to change this time frame and reprocess classification. I can just change the initial and final date and reprocess all the data and change the region and reprocess the classification. So the classification that I'm doing, if I don't limit, it will classify the whole world. And the new uses that we see using Google Earth Engine is loss of snow in the whole world, global tree deforestation, that was the loss of forests in the whole world. So we have more time we need more time to build the logic, the methodology, and then we can apply more time to analyze and parameterize the product, the final product. That's it. Thank you.
Thank you very much, Marcos. And now we have some comments from Professor Reinaldo.
I'm allowed to make questions as well. I am allowed to make questions as well. Okay. Well, first I would like to thank the opportunity to be here, and it's a great responsibility to make comments on such two very brilliant presentations. And actually, there were classes of the use of remote sensing, not only in geography, but in general to urban studies, and in particular related to health issues. So I'm going to start with what Chris presented. It was, I would like to thank you very much, because it was very clear and didactic way to present remote sensing and all the things related to the practical use of remote sensing. And that is something that makes me very happy, because it raised the importance of geography for everybody, not only for geography students, but it makes very easy, from my point of view, to understand things which are very complex, like spatial resolution or spectral resolution, or even the time resolution, the temporal resolution, I forget the name. I'm not going to go inside other kinds of resolution, there are more, but it's enough with that. So the importance of the field to work with this study, so it shows how geography is great. So I would like to make this commercial, because I'm a geographer, of course. Chris also point, even though he didn't stress this point in a specific way, but he points his presentations in things that you cannot see from space. Like when he mentioned the field work that we make some years ago, and the observation he makes of how the buildings in the periphery of São Paulo, they had a lower appearance that looks like older, and it shows clearly that people had stores on top of this. So it might look, which this is not important, but this really, really very important observation, because it shows how you have to be aware that you have to go to places to study. Geography comes from the part, how do you call this part of your feet? The sole of your feet. Oh, that's the words of a very known Spanish geographer. But it's true, you have to go to the fields and to understand the things and see how it behaves, what you are going to study, the object of your study. And that's very well known in photogrammetry from old times. And people usually are not aware of that. For example, when you see a map that was made by a cartographer or photogrammetrist, he takes the photograph of the city. In a map, there are a lot of things that they were not catched by the camera. Like, for example, the name of the street. You can take the best photography and you never see the name of the street. So you have to go there and to make research. And the same thing is demographics. And that is why this kind of studies can add to what we are doing now, which is to combine all these interdisciplinary approaches to better understand the city and to take more advantages of the tools that the new techniques can give it to us to make this work happens. And that is why I think that both of the speakers coincide. They use the satellite resources in different ways, but to easy our lives, the researchers' life, or the public, general public in general, to acquire that information that otherwise is very difficult to get. On the other hand, it's also very important what Marco has just mentioned, which is the global approach. It is a new time for science. It's not more the time what the researchers make a very specific research on the ground where he is studying. It's not the problem of being comfortable with your space. It's the problem that the humanity needs to understand the process in a global way and to make a classification that what he has done is very important because it goes to take the same parameters, make it work everywhere in the world. So that is very, very difficult to acquire, and that is also very dangerous, Marco. Yeah. You have got into something I was commenting with Chris, that to make on-the-fly classification is very dangerous. You can refer to Bill Gates, Steve Jobs, when they make their presentations and something goes wrong. It's very easy that something goes wrong. So, but you succeed with your presentation, so I was very happy for you. And I found that the work you have been done is great. It's very tough work. There is a lot of hours behind what you are just presented in a few minutes. And the same was what Chris have been done in the last few years, because you use the global parameters that Chris developed in the past for the same purposes. That is to develop global parameters capable to analyze the urban separation of the linear spectral mixture model in different parts of the world. So I think that is the most important thing. So I will end up with a question for you both. Is that how do you think that these studies can help us with the urban studies to go into more deep analysis of not only the health on the city, but also from the comfort of the people who live in cities. Thank you very much.
Thank you. Thank you, Reinaldo, for your comments and questions. I will ask to Marcos to answer the question after Chris.
Okay. First thing that we need in geography is have data to plan, to understand what's happening. This kind of classified data can show us the historical land use and how it's being densified in some region, what we have left of vegetation, forest, and and open fields where we can grow, show the dense areas, that's favelas, that's the areas that has no other infrastructure, no space to grow. And this may be used to plan, to understand the city and to plan how to act to improve the actions of the government and we have to do in the city. So we have to build this knowledge, and with this Sentinel with 10-meter resolution, with images each week, we must have a way to analyze all this data. That's important. We are producing a lot of information that we have to, a lot of data that we have to convert to information. And that's what this classification method and this cloud processing may allow us to do in the near future, and today it's already doing that.
Thank you.
Thank you, Marcus. I just forget to mention something that is also, it was also acquired by both of you. That is the differences between the Landsat imagery and the Sentinel-2 imagery. That is not only a problem of spatial resolution. People tend to grow into the tendency of if it is greater resolution, greater spatial resolution, it's better. But it's a problem at the same time, because when you have very high resolution, very high spatial resolution, then you see more things. And when you are going to classify more things, this is a vicious circle. You go into the classification, and then there is also a danger that you have been solving quite well, that I have experienced myself, and I think that Chris as well, that when you go into classification, you try to classify everything. And then you are addicted to classification. So you try to go deeper and deeper, and if you don't break that, you never get out. So that is the danger of the classification when it goes very deep. The other thing, on the other hand, is that the Landsat satellite imagery, it goes 30 years back. And this is incredible. There is no other source of information in the Earth with 30 years of images from all over the world. And this, on the other hand, Sentinel-2, it is only 2 years or 1.5 years. But then it comes to the other resolution, which is the temporal resolution. The Landsat imagery, it is 16 days, but don't fool yourselves. 16 days is in the paper. We know that we can take, if we are lucky, 3-4 images per year of a region which is like Sao Paulo. It is not very much clouded. In the Amazon, is none. And that is why he has to remove the images. And that is one of the dangers of the thing. And the Sentinel-2 is 6 days. So the chances to have more images good in 6 days is 2.5 more than the 16 days. And Chris just told me that in Sao Paulo, in South America especially, the Americas in general, because Sentinel-2 is an European satellite. Of course, they start with their place, not our place. So now, if we are lucky, we get, how much? 3 images per year, more or less?
For Sao Paulo, yeah. Maybe 4 cloud-free images as of a week ago.
Okay, so you see, 4 is almost like the average of Landsat. So, but then you have to take into consideration which is the good things, because satellite Sentinel-2, it has 13 bands. So this is the 3rd resolution. Then Chris didn't mention the word, but this is the spectral resolution of a satellite. While you have 6 bands or 5 that we use for Landsat, for Sentinel you have 16. So, you know, you gain from one side and you lose from the other side. So what you have mentioned, yeah, both are free. That's also a very important point, because the people who are older, like me or like Chris in satellite research, we remember when the satellite imagery cost $3,000–4,000.
$4,400 per scene.
You see, that is capitalism.
And the company that had that was given ownership of the data went out of business. Even with the U.S. taxpayers paying for the satellite, that company couldn't make a profit.
So,
Okay, Chris, would like to comment a question from?
Sure. I'm going to go back to your original question, and I like you asked the same type of question that I like to ask, except you ask it much more politely. I usually just say, so what? Okay, so we can map so buildings cast shadows, and it's hotter on the sides of the buildings than it is on the street, so what? Who cares? And if it's presented the right way, it may even seem obvious. Yeah, sure, tall buildings cast shadows, they intercept sunlight. You don't need a satellite to see that. So what difference does this make? The difference that I hope it makes is that by understanding this, by measuring this process, and especially by being able to go back through time and look at how these cities have evolved in ways that we can't do any other way. As Rinaldo mentioned, for most places, we don't have this type of information going back this length of time from any other source. And if we're able to use it to understand more deeply the processes, for instance, what is the real effect on air temperature of 2 extra hours of sunlight on a street? How much of a difference does that make on average of the air temperature at 11 o'clock in the evening? That's a harder question to answer, because we don't really understand yet the nature of the energy balance at the street level. We understand it in a very simplified way, but until we're able to measure it, we don't necessarily understand the details. And so why I think this might be useful in the future is, and this is, you can generalize this idea to the use of classifications like what Marco is talking about, is that the environment that we live in is, I often prefer to refer to it as the built environment as opposed to urban, because the word urban has so many different meanings to so many different people. And the thing about the built environment is that we construct it. And so we have the option of building it in certain ways that may make a difference to how it functions. And so by taking into account, for instance, the effect of shadows and solar illumination, we're not going to tear down all these buildings and build them all over again for that reason, but at least in New York, and I imagine it's similar here, real estate's being purchased and buildings are being torn down and rebuilt for other reasons. But if the people who are making the decisions about how to rebuild the buildings have a little more understanding of, for instance, how the building reflects light. If you think about it, in New York at least, I haven't been, this is my first time here in the actual winter, and I've never been here in your summertime before. But in New York, the difference between our summers and our winters is pretty significant in terms of temperature. And so in the summertime, we really don't want the streets absorbing any more heat than they have to, because it makes it very uncomfortable for us in the evening. We're not as used to the high temperatures and humidity as you may be. But in the wintertime, it's a different story because it's cold. And so we may want to capture that radiation in the wintertime. Now, it'd be nice if we could afford to put solar panels all over everything and just capture it and convert it into electricity, but we're not there yet. But if you can imagine movable reflectors on the outsides of buildings, and I know some places in the tropics they do put reflectors over the windows to reflect the sun back up. Well, so in the summertime, you might want to have a light surface reflecting that incoming solar back out into the atmosphere. But in the wintertime, you may want to flip that reflector over and have it absorb the radiation and use it to offset your heating costs. And something like that might not be that expensive relative to the cost of building an entire building. If we knew a little bit more about the effect of this incoming solar radiation, we might be able to do simple things like that, like build a component onto the building that captures the radiation at one time of the year and reflects it back out at another time of the year. And so what? Maybe that might make a difference. I don't know. But in the meantime, it's provided me with a great excuse to come down here and spend 3 weeks in Brazil. So from a personal perspective, it's working for me. Thank you for hosting me. I'm very happy to be here.
Thank you very much. I don't know if you have time for questions from the public. Okay, so if anyone would like to make questions to the speakers.
Thank you for the wonderful presentations. Really fascinating, and you're right, geography is great. I'm a biologist. My question, I have many questions, but I think one of the questions that I would like to ask today is whether these tools that you are inventing and using could somehow be used to learn what is going on in terms of global warming, and more than that, maybe to model what is going to happen in the future in terms of not only temperature, but the shadows as well and everything. Maybe that could be modeled. We have in the IPCC now a report that has to be released in 2018. That is what is going to happen if we cross the 1.5 degree. And this is really very important. I think the geographers, well, from what I saw, I think the geographers, they have a very, very good tool to help the planet to understand and be prepared for adaptations in the future.
Who? Chris?
So one of the areas where I do field work is in the southern Arabian Peninsula in southern Oman, and not urban there, where we're looking at grazing issues in the mountains. And so the last couple of years I've spent a couple of 6-week intervals there doing field work, and I wish I could say I had learned to speak some Arabic while I was there, but Portuguese is difficult enough for me, and Arabic I think is probably not realistic. But I did learn one Arabic word that comes in handy, and in part because it's used in maybe every third sentence that you hear anybody utter, and it's the word inshallah, which I don't know if you're familiar with this word or not. It means God willing. And so I think about this a lot, not only when I'm modeling things, very simple things like illumination or spectral mixing, but when my colleagues on the floor below me are running coupled ocean atmosphere models and running them 20 years into the future. And I think that, and I remember hearing that in some parts of the Arab world, people used to become incensed when weather forecasters would come on and say what the weather was going to do tomorrow with certainty, as opposed to acknowledging the uncertainty in a weather forecast. And so I think the same thing applies even more so with climate models that are basically trying to run weather, effectively weather, integrated weather out years into the future. And so I always, whenever I hear the word will, I substitute may. And but I think one of the keys to, and one of the things that has made weather forecasts improve so much in the last 20 years has been, one, the ingestion of a lot more data, a lot more observation is used in near real time with weather forecast models now than was the case a few years ago. And this has had a big impact on improving the predictive skill of the models. And so the information, the data that we're collecting and the information we derive from that, I think certainly must help, or it will hopefully help, and it certainly shouldn't hurt the forecast skill of the models, because if it helps us understand the processes going forward, then that may be valuable. And then two, even if we don't ingest this information directly into the models, if it helps us understand the physical processes at the scales where they occur, and so I'm talking about microclimate now. You know, we know a lot more about macro scale climate than we do about microclimate, because until recently we didn't have tools for measuring, for instance, those surface temperature, the street level scale surface temperature images that I showed you. It wouldn't have been possible to collect images like that even 10 years ago. And so now, maybe by being able to study the processes at the scales where they affect us more directly, at street level scales, that may also help us going forward. Sorry, that was a longer answer than I intended.
Just quickly to add some, this land use cover that we are doing for Brazil from 1985 to 1917, it's an initiative with the Climate Observatory to check the gas emission from Brazil and to monitor it in the next years. But all this data is then put to any model. So having this data as classified data is a very important input to model the future.
Please, question.
Thank you. First of all, congratulations for the panel and the presentation. It's a very interesting issue. And I was really puzzled by something you said, Christopher, when you said that buildings have the potential of delivering environmental services. And now with your explanation, you said how you can handle buildings in a way to increase or reduce the warming of the cities. This is extremely important and can have a huge impact on the real estate industry. Had you had the opportunity to talk about this with the real estate industry or with some mayors and some cities in a way that this science you're working with can influence the way we plan cities into the future?
Thank you. I'll try and give you a shorter answer this time. Yes. The short answer is yes. I've had the good fortune to live in New York and to have had students who have gone on to work for different parts of the city government. And so I've former students who are now in the upper levels of the New York City Parks Department, Department of Environmental Protection, and the Office of Emergency Management. And so so I've been fortunate in having direct contact with the New York City government this way, and more importantly, the good fortune of living in a city that has surprisingly enlightened leadership in terms of environmental issues. There are a lot of areas where the leadership in New York is not always as good as New Yorkers might think it could be, but in terms of environmental issues, New York is, and geospatial issues also, New York City government is way ahead of the curve. And so they do take into account things like this. The Mayor's Office of Sustainability had used this kind of information to such an extent that in 2011, the New York City Council passed a law requiring that newly roofed buildings, that the roofing materials not only pass a reflectivity standard in terms of being reflective, but also an emissivity standard, which is the physical characteristic of a material that determines how easily it absorbs and loses heat. And so that's an example, and that I wish that I could say that I was the one who recommended that, but the point is that the government, New York City government, had the good sense to hire scientists on the staffs of their agencies so that they're aware of things like emissivity and the fact that you can easily add that to legislation to require that newly roofed buildings are not only more reflective but also more emissive, and so that they don't store heat as much. So I think that's a good example of at least a local government being, I think, kind of enlightened and using this sort of information. So.
Any more questions? Please.
It's interesting. First of all, geography is indeed fascinating. And we had just the opportunity of complete a global comparison on the effects of temperature on 382 cities in different latitudes. And cities do exhibit variations in their resilience to thermal variations. In New York is much more affected by heat than for cold, so it's prepared to deal better with cold and heat. Some cities like London, even São Paulo, Rome, are non-resilient to both sides. And so those studies were conducted using the average of the city. Do you think that you have the capacity of building different cities within a city and then use this variation and coupling with mortality, the corresponding mortality, or dividing the cities in zones as classified by your classification, see whether if the average is reflecting, so you show the city is unevenly prepared or reflective to energy. Does it correspond to health effects in terms of premature mortality? Do you try to combine mortality or morbidity data to your findings, conducting different time series, taking advantage of such variation?
We did not try it, but it's very possible to do. Like, we have a very different scenario from Jardins to Brás and to Paulista, and it's very clear to separate this in the images and in the resulted maps. But that's interesting.
I think that so I'm trying to, as Ricardo said, there are many possibilities of here. One is establishing sound policies, but I think if you, in addition to the market, to the real estate marketing, or you can use this as a new tool to use the. So I'm challenge us to. I think I am a pathologist, so I understand is my topic of interest. So, and they are in evenly coded. You know, there is no variation across the of temperature among the deaths. But I think that if we can measure vulnerability or transform those, so we can point out specific points of the city that urban intervention should be applied or being a subject of preferential law enforcement to solve the questions. I think that Ligia and you, if you are daring to do this, and we can have provided this long-term mortality data. We have mortality data in São Paulo from very good data with geocoded, so with the address in the last 20 years. São Paulo has one of the best time series information of data disaggregated by different endpoints. So I think we could try to see whether people respond differently in those categories. So doing something different. Perhaps this could be a task. Thank you. Just to finish one thing. I would like to call. Also, there's another question.
Good morning. I would like to thank you for your presentation. I'm Lucas from the Master's Program in Human Geography. And I would like to make my question for Professor Christopher. How thermal consequences can be related to health aspects in the city? For instance, the shadow observed in the very city center, where the uses of the territory has a different process than areas such as Paulista Avenue or other modernized areas. And I would like to know if the presentations will be available after. Thank you.
Okay, I will pass to Chris, but just remember that our time is over, and I ask you to.
Short answer, yes. My understanding, the presentations will be available, I think. I'm trying to think of a short answer to the first question. And one thing that I notice in New York in the summertime is that it's very easy to tell. New York, like Sao Paulo, has people from all over the world. And it's very easy to tell in the summertime when you see people on a sunny day who has come to New York from the tropics, because they walk on the shaded side of the street and they stand in the shade of the trees. The people with blonde hair are walking in the sun, sweating profusely. And I'll walk quite a bit further if I can do it in the shade in the summertime. Whereas you see people do exactly the opposite in the winter. More people walk in the sun, mainly people from the tropics, I think. So I think on the street level, some people figured this out themselves. Other people just don't think about it. But if it's as simple as making more shade available, if that reduces the stress on people who have to walk outside anyway, there may be inexpensive ways to do this that could be easy to implement.
Okay, thank you very much for coming, everyone. And I have to finish the panel now.
I have a small ceremony.
Okay.
Just a small ceremony. I would like to give this certificate to Flávia Morato Kawakubo. It's the first document. We have a lot curriculum, so she will receive this the certificate. So I think this is the Guinness record for the latest curriculum. And so So, Flavia, this is your certificate of participation. It was an honor of having you here.
Okay, thank you very much.
Geo.
Yeah.
So this is geography is too far advanced, you know.
Okay, thank you very much, everyone.